All right. So this is lecture 6. Let me switch to the board and we can start. All right. So this is lecture 6. And today is 12th of April, 2122, right? Hard to believe. Okay. So, so let's see where we are. We have been so far we have been discussing how to model a structure as a single degree of freedom system. In other words, how to set up this model, right? To find the equivalent stiffness and the equivalent mass. And the approaches that we have discussed were what so far? Using second law of mechanics, which if you use the lumbar principle, it reduces to setting up the free body diagram and deriving the equation of motion. Deriving the equation of motion. And by setting up the equation of motion, whatever is the coefficient of the acceleration term is k mass equivalent, whatever is the coefficient of the displacement is k. And even if you have damping, whatever is the coefficient of u dot is that damping coefficient, right? The second approach we introduced was, I call that the structural analysis, or better call that simple structural analysis. Okay. In finding or setting up the equation of motion and finding these coefficients, stiffness is usually the most complicated one. And the stiffness has nothing to do with this dynamics, it's a static property of the system. So we introduced a special case when you have the stiffnesses or springs are in parallel or series, okay? That was for a special case. But today I want to demonstrate that if that is not the case and we have even a more complicated case, by using direct definition, okay, of stiffness, you can find the equivalent stiffness in the system, okay? So before I do that, let me refresh your memories about the concept of stiffness, which I've, of course, said that before, and I may be repeating myself, but it is important in this context, which is a second approach, remind you again. The stiffness is what? Stiffness is the quantity that relates force to displacement. Is a static quantity, right? And in order to find that, let's say if you have a beam, okay, with a mass at the tip, this has these uh, properties. How do you find the stiffness of this beam? One approach is, okay, by saying that, okay, a stiffness is the force causing a unit displacement. Okay, so what is resisting the displacement of this mass here? If I want to find an equivalent stiffness, which is resisting this mass here, which is the stiffness of this beam, what do? I say, okay, this beam under the action of a force at that degree of freedom, but that's what we're interested, right? Which is the tip of the beam. If you apply a force at that degree of freedom, F, this experiences a deformation. This deformation caused due to that force is FL cubed over 3EI. So the force that causes a unit displacement is the stiffness. If that means if this is 1, this would be the stiffness. So the stiffness of this beam is 3EI over L cubed. Okay. You can use that, of course, to find the equivalent stiffness of other types of beams, for instance. Okay. If you have a simply supported beam, you want to think of, okay, let's say you have a lumped mass here in the middle, so you're interested in the displacement at this point, or the degree of freedom being this, right? What is resisting this motion here, as far as the stiffness of this beam goes, we know that if you apply a force F, this displacement is, uh, 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 you know, what is it? 48 EI over L cubed is F L cubed over 48 EI is this displacement delta. So the simplest supported beam acts like a spring that the stiffness of that would be 48 EI over L cubed. Okay. But many times they finding the stiffness is not as easy. So instead, we may use the concept of flexibility. What is flexibility? Flexibility is the inverse of stiffness. What does that mean? That is, flexibility is the displacement due to a unit force. So if you, in this beam, for instance, if you apply a unit force and find the displacement here, okay, that is called flexibility. And let's show that with this, okay? So it's the displacement due to a unit force. Let me demonstrate this concept through a simple problem and show you when you have a complex case, how you can use this approach to find, derive the equation of motion and find the equivalent mass and stiffness in a system. So let me look at this example. Okay. Any questions so far? Okay. Let's say you have a disk pinned at its center at point O. You have a string or a cable. So say a rigid cable or string, massless, attached to this point A, and this cable is holding a mass M. Let's say this disk is massless, and you have at some point B a spring attached to this disk at a distance of a from the center of this disk. And this disk, this mass starts to oscillate, going through a displacement u of t, and you want to set up the equation of motion, or in other words, find the equivalent mass stiffness, so you can set up the equation of motion for this system, which is mu dot plus ku equal to 0. So what is km and what is this? Okay. So let me also say radius of this is r naught. You can see that if you want to use method 1 or method 2, which is this parallel of springs or series of spring, you cannot do that. The approach 1, which is setting up the using second law and setting up a free body diagram, you can do it, but it's not going to be easy to use that to derive the equation of motion. What I will do, I will say this. If I look at point at here, M, okay, and this is going through go back to the definition of flexibility, displacement due to a unit force, okay? So if I apply a unit force on this mass, okay, since this is inextensible, whatever deformation this goes through is the deformation that A goes through. So in other words, it is as if I have applied this unit force at this point A, okay? So let's look at what happens. If you apply this load here, what happens? This uh, spring is going to stretch, go from here to this point. Let me call the displacement of that spring A. And this point O will rotate. Let me call this angle phi, which obviously would be the same as this angle. Okay. So let me look at the free body diagram of what happens right now. So this is point O. These are the two forces. You have, if this is going to rotate due to the action of this unit force, okay, going from, this is point A, going to point A prime. This is phi sub A, okay? Let me call this displacement, which is what we want to find, delta A, okay? This spring is going from B to B prime. This is delta. So you have a force of F of K here. You do have a unit force here. These two forces, okay? So this is the free body diagram of this disk, right? The disk, of course, is massless. The only forces are these two. If I look at this free body diagram, delta A is the, remember again, is the displacement caused due to unit displacement. If I find delta A is the same as the displacement of mass, because this is inextensible and massless. So whatever displacement this goes through, this will go through. So if I find delta A is the flexibility that is basically resisting the motion of this mass. But let's do that. So I will take summation of moments about point O here. This distance is A. So I have the force in the spring times the moment arm A is equal to this distance times this force, which is 1. So in other words, force in the spring comes out to be R 0 over A. Okay. However, I mean, you do know that this is going through a displacement, right? In other words, f of k in terms of displacement that it's going through is what? It's k times delta, or delta is f of k over k. Okay. But wait a minute. This is the angular rotation, right, of any point on this disk. You see that from this triangle, in this triangle. If this is phi, I can relate phi to this delta, right? In this triangle, you can see phi is what? Sine of phi, of course. Sine of phi is delta over A. Angle being small, that means phi is delta over A, right? So if this is the delta over A, okay, I would now substitute this in this delta A. But what is the relationship of delta A and phi? Delta A is what? In this triangle is R times phi, okay? Or in other words, is R times delta over A. Delta is f of k over A, right? Delta is f of k over A, over k, I'm sorry, f of k over k. So I would substitute for that, for times f of k over k, okay? Now, if I substitute for f of k now, f of k was R naught over A. So this is R naught over A. So delta A becomes R naught squared, right, over A squared K. Okay. But what is delta A? Delta A is the flexibility, because as I said, it is the displacement caused due to unit force. That means the stiffness of this system, okay, is what? Is 1 over delta A, which is A squared K over R naught squared. So this is the equivalent stiffness. So if that's the equivalent stiffness, right? So what do I have here then? I have, uh, this is the equivalent stiffness. That's the mass that's going through this deformation. So equation of motion would be mu double dot plus a squared over r squared k times u is equal to 0. That is the equation of motion. So this is the equivalent stiffness. This is the only mass that we have, m equivalent. So if you want to find the natural frequency of this system, would be what? K equivalent over mass equivalent, the square root of that. So would be simply A over R times K over M. Any questions? Very simple, right?
Actually, quick question on the sum of the moments equation.
Mhm.
So on the left, I get why you have the spring force times A, but on the right, is that R naught times 1?
Yes, because you have a force of 1 at this point.
Oh, okay, we define the force as 1. Oh,
Right,
because we were
exactly.
doing flexibility. Thank you. Sorry.
Exactly, flexibility. So what we want to find is that displacement due to this unit force, displacement at A, right, is due to the unit force would be the flexibility at A. And this is inextensible. So displacement at A is a displacement of M. So the flexibility would be at A the same as the flexibility that is resisting M. Okay. All right. So
Can I ask
I'm
a?
sure though, yes.
I was just gonna ask, how do we know not to include the D'Alembert force on this one?
Oh, see, good point. Very good point. See, what I did was I just completely did away from using the second law. I'm just using simple structural analysis. If you, what you're saying is that, okay, if this is going down, that's your question is, if this is going down, you have mg, right? That's what you're saying, right?
Yeah.
Right. So downward, I'm assuming if the displacement is very small, and then you're starting the motion from the equilibrium, that is, the stiffness has already, due to the application of M, has already been stretched going through its static displacement. So the configuration that I'm showing you here is from the point where this stiffness is going to be now stretched after it has already gone through the static displacement. Then so you apply the mass. Now from this point, I'm going to measure the displacement. So the uh, force of gravity doesn't come into picture. It's the
Okay.
same concept
Yeah.
that we, okay.
Okay.
Any other questions? All right. If not, let's now, uh, you know, let's now move on. I am positive that you you would ask this question, how about if this is more complicated? You have a much more complicated structure. How do I apply this approach? What my answer to you is this. Okay. Method one and method two, in other words, the second law and structural analysis, or the simple structural analysis that we introduced so far, are not really a very general approach to derive the equation of motion. They're only applicable to cases that you have a simple system and you can either easily set up uh, the free body diagram and apply the second law to find the equation of motion, or using the concept of parallel or series of springs or simple structure analysis, set up the equation of motion. The more powerful approach, which I'm going to introduce, which is the third approach, is the concept of the conservation of energy or conservative systems. You remember from your physics that if you have a conservative system, that is, energy is not dissipated or gained in the system or stays constant, sum of all energy stays constant, you can write kinetic energy and potential energy, some of them being a constant value, as long as you don't have any other forms of energy like heat. This simple relationship is a very powerful approach, in fact, to derive the equation of motion. And I'm going to demonstrate that. Okay. Let's use just this. First of all, what is kinetic energy? Kinetic energy is 1/2 of mass times the velocity squared, and potential energy is 1/2 k times displacement squared. Okay, that's the definition. First, let me show you just based on this simple concept, how we can even simply derive the equation of motion for that single degree of freedom system that we had set up without using second law or definition of a stiffness or whatnot. Okay, so let's just derive the basic equation of motion using energy. So if you have a mass experiencing displacement u, it's obvious that the kinetic energy of this system would be 1/2 mu dot squared, right? How about the strain energy or the potential energy? Potential energy would be potential energy of this is spring. So if this is spring is experiencing a displacement u, okay, and obviously this is a linear spring, this is the this is if you in other words if you have the force applied to this and this goes through a displacement u, okay, what is the strain energy or the potential energy of this spring is the area under this curve, right? This is K. So it would be 1/2 times K U dot. Okay. So that's the kinetic energy, potential energy of that uh, spring. So this is 1/2 K U dot. So what I would do is by using this concept, that means the time derivative of a constant value is always zero, right? So the time derivative of the sum of these two should be zero. So that's what I would do. I would take the time derivative of the sum of these two terms and equate that to zero. But what is the derivative of this with respect to time? This is a constant. So the only time derivative I have is for this, which would be 2 u dot u double dot. Same thing here. This would be 2 u dot u. So if you substitute that, the time derivative would be 1/2 m times 2 u dot u double dot plus 1/2 k times 2 u dot u is equal to 0. Since u dot is not 0, I can divide both sides by u dot, right? And you can see quickly that this is what this derivation leads to. So I could derive the equation of motion without the need to use the first two approaches based on this simple concept of conservation of energy. Now, let's demonstrate this. In fact, how you can do uh, the same problem that we did, or in fact, even a more complicated case of the more complex form of the problem that we did using this approach. Okay. In other words, I want to demonstrate that this problem, how you can do that with, using this approach. So let's do that. In fact, I'm going to make it even more complicated. So let's say you had that disk, and I'm not going to ignore the mass of this disk this time. So this is like this. You had this mass attached to this. Let me call this mass 1 because I'm not going to ignore the mass of this disk, which I did before. So this is mass 2, okay? So you had this spring attached to this. This was the stiffness of that spring, okay? Now, I want to derive the equation of motion. So forget about all those assumptions I made. Okay, what I want, okay, again, of course, this is rigid, massless string or bar or whatever. So we said that if this is going through a displacement u, that means point A will experience the same displacement u. So u at A is equal to this. So let me call this rotation as before, phi at A, which is the same as this phi, okay? This distance was A, and the displacement that this spring would experience is delta, okay? All right. So I want to derive the equation of motion in terms of u. Radius, we said, is r naught. So u was what? R naught phi, okay? So I don't need free body diagrams. I don't need anything. All I need is what is the kinetic energy of this system? You have two masses, this one and this one. What is the kinetic energy of this? Would be 1/2 m1 u naught squared. How about this guy? Is a rotational disk. So would be 1/2 I u I. This is going to rotation phi naught squared. Okay. And remember that I, and I'm not going to, of course, substitute, but remember I is 1/2 of m2 times r naught 2, if you want to substitute for that. Okay. So that's the kinetic energy. How about potential energy? Potential energy is potential energy that this spring is experiencing, which is 1/2 k delta squared. You may say, how about the potential energy of this mass? If u is very small, okay, u is very, very small, I'm going to ignore that mg times u, which is that potential energy of this mass, okay? So you only have the potential energy of this spring, which is 1/2 k times delta squared. But delta was a phi, right? So this becomes 1/2 k times a squared phi squared. So that's the potential energy. Okay. So all I need to do is now set up this equation. Take the time derivative of t plus v is equal to 0. That is time derivative of, okay, 1/2 m1 u dot squared plus 1/2 I phi dot squared, okay, plus 1/2 k a squared phi squared. Equate that to 0. That's what I need to do. In order to do that, first of all, I would set up this equation in terms of one of these two variables. You can set it up either in terms of u or phi. It's easier to substitute for u, which is r naught times phi. So this becomes d over dt of 1/2 m1 r squared phi naught squared, okay? And this one is I, 1/2 I, okay? Phi naught squared plus 1/2 k a squared phi squared equal to 0. So what is the derivative of this with respect to time? This is the constant term. So you have only the derivative of this, which is 2 phi naught phi double naught. Same thing here. This is constant. So this is 2 phi naught phi double naught. And here is only derivative of this, which is 2 phi naught. Okay? Again, phi naught is not 0, so I would divide both sides by phi naught. So phi naught cancels out. So simplifying this, okay, you get I plus M1 R naught squared times phi double naught plus K A phi is equal to 0. Okay, so you can see that this is the equation of motion. This is the mass equivalent. This is K equivalent. Okay, so of course, I, again, remember, is M2, 1/2 M2 R naught squared. So you can substitute that here if you want. You have 1/2 M2 R naught squared plus M1 R naught squared times phi naught plus Ka phi is equal to 0. Okay, so omega n, which is what you probably want to find, is Ka over 1/2 M2 R naught squared plus M1 R naught squared. Okay. Now look at this. If I put M2 is equal to 0, which is a problem I did earlier. You remember that problem? Let's see. If you put M2 is equal to 0, okay, you will see that this is going to, oh, I'm sorry, this is going to A squared here. Why did I put A? Okay. If you put M2 is equal to 0, this term would cancel out and omega n would be what? Okay, A over R, K over M, which is the special case problem that we did before. So you can see that using the energy method, I could make even the problem even more difficult by considering the mass of this rotating disk and yet derive the equation of motion so quickly and without any literally much effort. Okay. Any questions? No? All right. Positive, you have no questions at all?
Wait,
Okay.
sorry.
Yeah.
So we just have to assume that M2 is like the mass of M2 is, or like, can you just go over why we can simplify that into the special form?
Oh, the special case is the problem that I did here. In other words, I had a massless disk rotating, right? And I
Right.
used the flexibility approach and derived it, and this was the natural frequency. But
Okay.
I made the problem more complicated. I said, I'm not going to ignore this. And if I want to use that approach of flexibility, in fact, it would be a nightmare. But using the energy method without recourse to, setting free body diagram or using the concept of the stiffness and flexibility, I directly derive the equation of motion for the general case. But I said that in this general case, if you set the mass of the disk equal to 0, that's the problem we had done before. And you can see that easily. You can
Okay.
even, that's the whole point.
Yeah. Okay.
Okay.
I see now. Yeah.
Any other questions? All right. I did, of course, a simple form of this problem in the other section. And that was, in fact, a different, you can say different problem, but for the sake of having these on records, I did actually this problem in the first section, which is easier. So I assume that the spring is attached to this point here. okay? And so the kinetic energy was, again, of course, 1/2 m1 u dot squared plus 1/2 I v dot squared. But potential energy in this case is 1/2 k u squared, because whatever displacement A experiences, this spring would experience. So in this case, the problem actually takes a simpler form and becomes m1 r squared plus I, okay, v double dot plus kr squared phi is equal to 0. Okay, so this is a special case of that problem I did, but you can do that and derive this equation for yourself, because this is a simpler form than the problem I did. All right, so let's see where we are and where we are going again. We are focusing on energy method. So I did show you that using the simple concept of energy method, as long as you have a conservative system, by using the time derivative of the sum of the kinetic and potential energy, you can directly derive the equation of motion. Now we want to actually generalize this to more complicated or more complex systems, and introducing the powerful method of which is called Rayleigh's method, which is based on this same concept. Okay. So I will just set the tone right now today for introducing Rayleigh's method, and we will continue next time. Let's go back to what we had discussed at the beginning when we were introducing the concept of degrees of freedom. We said that if you have, let's say, a beam that consists of infinite number of degrees of freedom, okay, if you identify 1 degree of freedom, which is in this case tip of the beam, which is what our main interest is, the maximum deformation, you can always relate the displacement of every single point along this beam to this degree of freedom. And of course, we use the concept of a stiffness and came up with a representation of the single degree of freedom system for this beam. But what about if you don't have just one mass here? You may have a beam with multiple masses. What do you do there? Because each one of these obviously is going through a displacement, right? So in dynamic equation of motion that you want to derive or you set up, how do you relate these to this degree of freedom? Okay. This is what Mr. Rayleigh did, which laid out the foundation for, in fact, deriving the equation of motion using the concept of conservation of energy or the conservative system. He said, okay, let's start with a simple problem. Let's say you have a beam with 2 lumped masses, M1 at this point and M2, maybe at third of a distance from this tip of this beam, length of this beam being L, okay? He said that, okay, let's say this is a dynamic system and we want to set this up as a single degree of freedom system. What do you do? Well, he came up with this idea. He said, okay, if you have a beam subjected to a load P, static problem, right? And this beam is displaced at this tip, a value, I call that U of L, okay? What is U of L? U sub L is 3 pi, I'm sorry, is P over PL cubed over 3 EI, right? That's what UL, that displacement is. But wait a minute, in strength of material, we learned that displacement at any point, U at any point X, okay, can be derived in terms of this load. U at X, if you remember, go back to the strength of material, displacement, which you use, of course, this equation, right? Curvature equation. You call that Y, the displacement, downward at any point. In other words, what you're going to find is this U at X, right? So this is X. You want to find this, which is that Y double prime in strength of material. You derived this equation before. That was PL cubed over 6EI times 3X over L squared minus X over L half. If you go back and check this formula in strength of material, you see that's what it is. Okay? But wait a minute. What is this? This is that U sub L over 2. So I can write U at any point is equal that U sub L times this function, 3 over half X over L squared minus 1/2 X over L. Oh, this was cubed, sorry. Cubed. So displacement, static displacement, at any point along this beam can be related to the displacement at the tip of this beam. As I said, this is how Mr. Rayleigh laid out the foundation, okay? He said something very interesting. He said, how about if I assume that the same relationship, if as long as U is very, very small, how about if I assume the same relationship holds when I have a dynamic motion? In other words, if you have a mass M1 and mass M2 here, okay, if this is U2, okay, at X and T, and this is U1 at X and T, I can say that the same relationship, which I derived now for static, can be extended to dynamic case. That is, okay, I can write this is equal to 3/2 X over L squared minus 1/2 X over L cubed. By doing that, I can relate the degree of freedom at any point to the tip of this beam. Let me stop here because that's where I'm going to start next time. I just laid the foundation. So we're going to go over Rayleigh's method and show you what a powerful approach Rayleigh's method is to derive the equation of motion. I can, in fact, once we cover that next time, I will also introduce the first project that you're going to do. that I will give you a simple problem that you can derive the natural frequency of that structure using Rayleigh's method, and then compare that with the exact natural frequency that I will give you, so you can get a good appreciation for Rayleigh's method. Okay, I'm going to stop here. Any question? If not, I'll see you in my office hours.